Well, here we are, folks. We're in the section 3, and we're going to talk about systems of linear equations in two variables. Now, there's several parts to that. It's not as long as it looks. Systems of linear equations. Let's start at the middle, really. We're talking about equations. Second, we're talking about linear ones. That means if you graph them, you get a straight line. Next, how many variables? Two. Two variables are what give you linear equations, lines. And last of all, the systems part just means that you've got a couple of different equations and you're interested in what x's and y's are good for both of those equations. Which x's and y, or x and y's, are good for both equations at the same time. So maybe the ordered pair 6, 52 might be the solution for that system of linear equations. Two linear equations, one solution. That's your goal. It is not always possible, but usually yes. Okay, let's get going here. All right, there's our list of things we're going to do. And notice that we're actually going to get my pen here. Okay. Three ways we're going to solve these systems. First, by graphing to get an idea in our heads of what it looks like. What are we actually doing graphically? Second, we're going to use substitution. That's a little bit easier. And third, not as easy, but not too hard either, because sometimes you need more tools in your toolbox. Some guys, I'm sure, really agree with that. You can't have too many tools in your toolbox. Well, it works in math too. Number 5, what systems don't have exactly one ordered pair solution? Usually that's what we're looking at, or we're looking for. One solution, one ordered pair that solves both equations. And last of all, of course, word problems. Actually, that's a lot of what we're doing. We're thinking about what can we learn from calculus that will help us solve problems. This time, though, we're going to use systems of linear equations, no calculus, just basic algebra. If you got some of those extra skills that you didn't have a couple months ago, they're going to come quite handy. So let's go. So notice we've got two equations. They're both linear equations, and it's called a system of linear equations, or just a linear equation for short. The solution is an ordered pair, and the ordered pair that satisfies both equations at the same time. So what does it look like? Well, first of all, what's the solution look like? Well, let's check and see whether 1, 2 is a solution. If we put 1 in for x, 2 in for y, does that really work? So we'll put 1 in for this x, 2 in for this y, see if we get a -4. Then, if that works, then we'll put 1 in for this x, 2 in for this y, and see if that gives a +4. If it does, for both, then we've got a solution. So, put 1 in because it's the x coordinate, replace x with a 1, so you just rewrite it. Put parentheses where the x was, put the 1 in, put parentheses where the y was, and put the 2 in there. See if it works. So here we go. There's our first equation, and we're going to put 1 where the x is, 2 where the y is, and simplify. Use our order of operations, and wouldn't you know it, this one works. -4 equals -4. Now we're not done with this linear equation or this system of linear equations, because we've only checked out the first equation. But it's been good. So let's see. In the second equation, put the 1 in for x, the 2 in for y, and here we go. It works for that one too. Since it works for both of them, we have got a solution for our system of linear equations. Hooray! Here we go. Next, let's start with first method, graphing. This says, since we've got linear equations, that'll give us two lines. And if they have one common solution, that means when we graph the first one and graph the second one, they're going to cross at one point, some point. We'll just call it x, y. And that is the system solution. Next, let's give it a shot. Solve this one by graphing. So we want to find something that works for both of them. We'll graph both the x plus 2y equals 2, and we'll graph the x minus 2y equals 6, and see what happens. So we're going to do it the easy way. So we'll take equation number 1, and what we're going to do is find the x-intercept. Remember that? You set the y equal to 0, put that in your equation. Here's your equation. Put the 0 in there, and see what x you get. Since you get a 2, that means the line passes through 2, 0. Second, remember this is equation number 1. Now, for the y-intercept, set the x equal to 0. So you take your equation, set the x equal to 0. Solve that, y equals 1. That means 0, 1 is a point on that line. Graph both of those points, connect them with a straight line, arrows at the end, and we'll graph that as a blue line. Okay? First equation, blue line. Second, here's equation number 2. We'll get the x-intercept because it's easy. That means set the y equals 0. There we go. Solve for x. And we've got the point 6, 0. Then we'll get the y-intercept. Set the x equals 0. And there's the 0 in for x. Solve that for y. And we've got a second point on that line. We graph those two. Dot for both of them. Connect them with a straight line on our graph paper, not here, and we'll make that a red line for equation number 2. So here's what we've got. Here's the first equation, that was the blue line. The second equation, that's the red line, and they cross at the point 4, negative 1. 4, negative 1, right there. So that's a common solution. That means it works in both equations. Put 4, negative 1 in equation number 1, it's good. Put it in equation number 2, it's good in there too. So there's your solution for that system of linear equations. And I'll suggest that you actually try that yourself. Put that point in both equations, double check, and make sure that works. Okay, method number 2. Method number 2 is use substitution. So how do we solve linear equations by substitution? Well, I'll tell you before we get started, some systems say use substitution, and others tell you in their own way, not substitution, we'll try something else. You could always do graphing, but graphing is a bit inaccurate because you're not exactly sure where those two lines cross. You have a good idea, but not exactly. So, how about the substitution? Well, here's a system of steps that you can follow. I'm going to follow those with the example. Solve one of the equations, either one, it doesn't make any difference. Solve one for one variable. In other words, solve them so you see one equation looks like that, or solve one where you have x equals something. Notice 1y or 1x. That's important. For substitution, that's what you're hoping for. If you like substitution, and most people do really, then if you have this as a viable option, a reasonable option, this might be the way you want to go. Once you've got this, let's suppose you found 1y equals, and then over here you had some numbers and an x somewhere in there. Substitute that expression that you found in step 1 in the other equation. Now this will make more sense once we get to an example, but let's suppose this is the second equation and you had 3y minus 7, or 3x minus 7y equals 18. Then you take this expression for y that you found in the other equation, you put it in for where the y is in the second equation, and that will eliminate all the y's. You'll have nothing but x's, and you can solve that. We've practiced with that in the first chapters, chapter 6. Once you've got that set up, you've done the substitution, solve that equation for x or y, whichever variable is left. When you get that, take it back into the other equation and find out what the other one is. So if you've found x equals 7 in this one, take it in the other equation, and you'll be able to figure out what y is by putting this in for the x's and solving for y. Next, check it. Does it work in both equations? It should if you've done everything well. Okay, here's an example so you can follow this. Well, already we've got the perfect setup for using substitution. We've got 1y, I'll emphasize that here, 1y equals minus x minus 1. That means that this y value, anywhere you see it, could be replaced by minus x minus 1. It's the same number, that's why you have the equals there. So we'll take the second equation. 4x minus 3, instead of the y, we'll put in the x minus 1 because it's the same thing as y. And there you have something that you're ready to solve. All you have are x's and numbers. You can solve that. So you'll have 4x plus 3x plus 3 equals 24. Subtract 3 from both sides. I'll give you a 21 over here. You have 7x left over here. Divide both sides by 7. And there is your x value. But what's the y value? For systems of linear equations, we need an x and a y that work in both of them. Well, that's very simple. Actually, go back to this one right here where you started. It says y. Oh, wow. Isn't that neat? It's all set up. If I want y, all I have to do is take the opposite of x, right here, subtract 1 from that, and I've got my y value. So y equals minus x minus 1, but the x is supposed to be a 3, so y equals negative 3 minus 1. Y is a negative 4. We've got it. So our solution is 3, negative 4. And if you go back and graph them, which would be fun, really, if you graph the first equation, there we go. If you graph the first equation, graph the second equation on your calculator, you'll see that they cross at 3, -4. And that's how you do it, folks. That's all the steps. And there's our step number 2. We already found back here that one of the equations was solved in terms of the other. That means you got the 1y here, so you've got it ready for substitution. And this minus x minus 1, same thing as y. So you take that over to the other equation, put it in where the y is. There you have an equation of one variable again. Simplify, solve for x. Y is gone. You can do this. Once you've got it in, here are the steps. Ones we've already followed. And then, once you've got x equals 3, go back to the other equation and put 3 in where the x is. So here's the first equation. Put the 3 in for minus x. There we go. And there's your value for y. So the solution is 3, -4. So you're doing pretty well. Next, you want to make sure you check, double check this thing, because you think you've got it. Check. Use the ordered pair in both of those equations to make sure it makes each equation true. I'll let you do that. Third method. Why do we need a third method if we've got substitution? I understand that. Why do we have to do it another way? Well, because sometimes solving for x or solving for y gives us a big mess. It looks like we've gone to Italy and we're eating spaghetti instead of having something nice and easy to eat. So, rewrite the equations. Make sure both equations look like this. A, B, and C, as before, just represent real numbers. But notice you've got the x and the y on the same side in this order. You might as well do it the same way all the time to keep from getting confused. Something x plus something y equals some number on the other side. If you need to, now this won't make sense immediately, but what you want to do is you've got two equations. Let's put it this way. Here's your first equation. Maybe the other one has a different a. We'll use a small a. Plus a different b and a different c. So what are you going to do? Well, the goal is that what you're going to do is you're going to take these two equations, set them up like this, with the x's in one column, b's in another column, c's in another column. You're going to add them together. And what you want to do, and you have to make this happen, you want these a's to be opposites, so the x's disappear. Or maybe the y's disappear. That way you'll be back to an equation with one variable. You can solve that, back substitute, and get the full solution. Let's get on to an example so you can really see what's going on. So here's an example. First equation, second equation. Now, notice number one, that solving for x or solving for y is not going to be an easy affair. If you solve for y, for example, 3x plus 2y equals 48. Solve for y, subtract 3x from both sides, you'll have 2y equals minus 3x plus 48. And it doesn't look too bad so far, but then you divide by 2 to get y, and darn if we don't have some fractions ruining the day for us. You have negative 2/3 x plus, and that'll give you a 24. And then you'd have to take this that has the fraction in it and you put it in here where the y is in the other equation. Not nice when you're ending up using a whole bunch of fractions. No one really appreciates that. So what do we actually do? Instead, what we're going to do is this. Now, to make this one as simple as possible, but give you an idea of what's going on, I'm going to target the y's. So put your eyeball on the y column. Now, they're already opposite signs, plus and a minus, but if you add those, the y's don't disappear. You end up with a minus 6y. That's going to make you very sad. So we're going to have to change this. Look at the 2 and the 8. What could you multiply one equation by, or both equations by, so that these y's would eventually become opposites, exact opposites? Well, for this one, if I multiply the first equation by a 4, imagine we multiplied that equation by 4, then this term right here would be a minus, or excuse me, a plus 8y. And if we add this 8y to the minus 8y, the y's would be gone. How about that? Well, let's do it. We'll multiply the 4 times this first equation. See what we get. So the first equation becomes, this is the new first equation, 4 times 3x is 12x. 4 times the 2y is 8y. It's looking good. And don't forget to multiply all the way through. Halfway doesn't count. Don't ignore this 48 over here. 4 times this, 4 times this, and 4 times that. 192. Got that? Now, the second equation. This time we won't have to fool with it. We'll just leave it, because it's already set up. The y's are going to disappear on us. That's good. Now, if you set it up like this, remember, you want to write both of them so it looks like ax plus by equals c. We're getting close. So add the x's together, and you've got 21x. Add the y's together, 0, equals, what do you get? Well, let's see, 192 minus 24, because they're opposite signs. Subtract, we've got 8 there, 7, 6, 1, 168. And then we'll take that 21x. We want x, so we'll divide by 21. And of course, 168 also gets divided by 21. There's our x. Well, don't get too excited yet, come on. X equals 8. Finish it out. All right, we're halfway there. So our solution is going to look like this, but I'm not finished. I've got the x coordinate, but I don't have the y coordinate. What can I do? Well, it's up to you. You want to use equation number 1 or equation number 2. Either one will work. Now, for me, I'm going to use equation number 1 because the coefficients are a little bit smaller. So I'll rewrite this, 3x plus 2y equals 48. Now I just found out x was 8. So I'm going to bring that up here, and I'm going to put the 8 for the exit, where the x is. And 2y, we don't know what that is yet, we'll find out, equals 48. There's your first equation with the 8 put in for x. So you've got 24 plus 2y equals 48. Subtract 24 from both sides. We'll have 2y equals 24. Divide by 2 equals 24 over 2. And lo and behold, there's my y value. Now remember, the answer isn't 8. The answer is not 12. The answer is 8, 12. Our answers are ordered pairs. Now that's our proposed answer. Do we know it's true? Well, we think it is, But what we need to do now is take that, put it in the first equation, check it out. Is it a solution? Is 3x plus 2y equal to 48? If it is, keep going. Check it in the second equation. Is 9x minus 8y equal to negative 24? If it works in both, then we have ourselves a winner, folks. The ordered pair 8, 12 will be a solution for that system. And we did it by the addition method. In some books, it might give it a different name. One book I saw once said it was a linear combination method. Because what we're doing is, when we multiply by 4, we've got the same equation, but we're multiplying through by a certain number. We get the same x's and y's, but it's a different combination of x's and y's. Okay. Let's clear this so it's not hidden. Solution. So rewrite the equations, make sure they are x's in a line, a vertical line, y's in a vertical line, and the constants on the opposite side for both of them. Make sure everything is lined up. Make sure the equals are lined up as well. If you need to, multiply one of those equations like we did by 4. Remember, by default, we actually multiplied the second one by a 1. Some of them you might have to multiply the second one by a different number. You might, for example, we eliminated the y's, but you could eliminate the x's. How could you do that? Well, if I multiply the first equation by a negative 3 and the second equation by a 1, then the x's will become opposites. They'll both be negative. There'll be a positive 9x and a negative 9x, and they'll add to give you 0. What you'll have is something y equals whatever number over here. And one more caution, when you're multiplying through the equation, make sure you multiply all 3 terms. Don't leave out the constant over here. It must be multiplied by that same number. So here we go. You can see what we did already. And then take that number and substitute in the other equation. Actually, either one would work. There's your 8. We got them in the opposite order, and that's fine. Check and make sure it works in both equations, and you can do that. All right, so what have we done? Well, sometimes a picture is worth 1,000 words, as they say. There are 3 possible end results we might get from that system of linear equations. Remember, the system of linear equations mean we've got 2 lines. 2 lines. Now, if we have 2 lines, what could it look like? Typically, when you graph 2 lines, it crosses at one point like we see down here. Excuse me. Another thing that's possible, though, is maybe they don't cross at all. Maybe they're parallel lines, so they don't cross. If that's the case, then these lines don't have any points in common. That means you don't have any solution at all. If this was important that you get a solution, you're out of luck. No solution at all if they happen to be parallel lines. And third, if those 2 lines, now you can't tell very well here, but the blue and the red lines coincide. They're the same line. That means that any point on that line is going to work for either one of those. So you get infinitely many solutions, just the opposite of having no solution at all. But that can be good, that can be bad, depending on the actual application. So you might keep this in mind, go back to it a few times, and get that in your head as the graphical interpretation of what's going on with systems of linear equations. Okay, let's check out another system of linear equations. First of all, you can tell they're linear because you got x to the first, y to the first in both equations. They're linear equations, you got two of them, so you've got a system. Sometimes a place will put a brace around the whole thing, sort of as a collector. Now you want to solve it. Notice you don't see a 1x there, you don't see a 1y there. So if you're a substitution gal or guy, you're out of luck maybe. So what we're going to have to do is make the x's or the y's be opposites. Well, this isn't quite as simple as the last example, but it's doable. If you look at the 4 and the 6 here, the 4 and the 6, your goal is, think of 4 and 6. What would be the lowest common denominator if you're adding fractions? Well, it'll be a 12. Remember, look at the coefficients, 4 and 6 in this case. The common denominator would be 12 for fractions. You want to make these both be 12s, but opposite 12s, 12x and minus 12x. Oh, how can you do that? Let's multiply this equation by 3 and this equation by -2. Now remember, we're trying to make them both 12s, but opposite 12s. So this will make the first one positive 12x. This will make the bottom one negative 12x, and they'll cancel out. We'll have some y's left, but we'll take care of that. So what do we get if we do this? So 3 times 4x is 12x. 3 times 6 is 18y. And don't forget the other side. 3 times 12 is 36. You're in good shape now. Now multiply by the -2. There's a negative number, so be a little bit careful. -2 times 6x, -12x. That's looking good in the first column. -2 times 9y, -18y. And -2 times 12, -24. All right, they're all lined up. ax plus by equals c. You can just add them together. In the first column, 0. Okay, second column, 0. Third column, 12. Okay, what does this mean? Well, if you look at the top of the slide, you might get an idea. Remember what we're talking about up here. We're talking about an ordered pair in both of them that'll work. So this is saying when we take a 4 times the x value, 6 times y value, add them together, I should get a 12. Well, down here this says when you pick a good x and a good y, 0 equals 12. Well, guess what? 0 is never going to equal to 12, no matter what x and y you pick. So that means no solution. Bottom line, this is what you might want to remember. If you end up with an absurd statement like this, then there's no solution. And I know one of you is going to ask, what about, suppose it asks for, what's the solution set for this system of linear equations? Well, the empty set. Because there's no solution, there's nothing in there. Or if you want to use this, it's fine. But remember, do not write this for the empty set. That's not the empty set. This is a good answer, that's a good answer. So you do everything perfectly. If you get an absurd answer, that means you got no solution. That's the most important thing to remember. Let's clear the ink here. Erase all the ink. All right, so you can see what's going on. They did pretty much the same thing, didn't they? Now let's take a look at another one. This also gives us an idea of why sometimes we would use the substitution method, as well as telling us something else too. Now when I'm looking at this system, one thing I notice is there's a 1y there. If there's a 1y or 1x, I am thinking I'm going to do substitution on this thing, because y and 3x minus 2 are the same. So I'm going to take the second equation and write it, 15x minus 5, but the y is the same as 3x minus 2. And there's my second equation with a substitution. Now let's see what we've got. We've got 15x minus 15x. Negative 5 times negative 2 is a positive 10 equals 10. So what do I get? Well, the x's are gone. I end up with 10 equals 10. Again, we have to go back to what are we saying with this system of equations? We're saying that we're looking for ordered pairs that make all of these things true. When is 10 equal to 10? 10 is always equal to 10, right? That means that no matter what x and y you pick on either of those lines, it's going to work. It also tells you that if there's an infinite number of solutions, these are actually the same line. So it's like that picture we had with the same line, one on top of the other. That's what it means. So your solution set would be, now this is a little bit exotic, but maybe you can follow. We've got ordered pairs such that, and you can just use one of those equations. Y equals 3x minus 2, because they're really the same equation, or they coincide. All ordered pairs across the board that are on this line are going to make both of those true. Okay, and you can follow that if you want to. That's basically the same thing we did a couple minutes ago. Now here's something that I'm tempted to cut out of this video and send it to my business calculus people. This is definitely talking about revenue and cost, and also profit, by the way, because these three concepts all go together. Revenue, cost, profit. Revenue is the money coming in. Cost is how much we have to spend to run our business. And profit is what's left over at the end of the year. Do we get to take a vacation to Italy, for example? Well, maybe we will if we have enough profit. So here's our revenue function. R for revenue. That makes sense. X represents how many items we're going to sell. TVs, for example. Put something tangible in it. This would be the revenue, or the money coming into our cash register if we sell X TVs. How much actually does come in? Well, this is how you calculate it. How much are you selling each TV for? And how many TVs are you selling? That's how much money is going to be coming in. That is the revenue. Sometimes you might see it like this. This is the number of items. And this is a price per item. The cost, excuse me. How is the cost figured out? Okay, first of all, think business. You're running your business. Things like air conditioning and insurance and so on are the same bill every month. So your cost for the month of September, for example, would be those fixed costs together plus how much it costs to actually make your product. The more of that product you make, the more it's going to cost you. Of course, you're going to make it up by selling them. Cost function. Fixed costs, like rent, for example. Maybe you rent your building or you have taxes on it. Those are fixed costs every month. Then the variable costs are how much it costs per item. Sorry. Last of all, the break-even point. That's where the revenue and the cost are the same. In other words, revenue equals cost. That's the break-even point. And you can graph those and see where they cross. See where you end up making zero money. Now that's not terrible, because remember, you could have so many costs that you would actually be losing money. So break-even sounds good if you think of that possibility. Now, another formula that you might want to remember even more than that is profit. Well, how do you figure out the profit? Well, it's the money coming in, called the revenue, minus the money going out, the total cost. That gives you your profit. And if the profit equals zero, there's your break-even point. So two different ways of thinking of breaking even. Either profit equals zero or revenue equals cost. So how does this work? Okay, you want to find the break-even point. First of all, the fixed cost is $500,000. You're talking about some serious money here. So first of all, what's the cost function? What are we going to have to pay? Well, before we produce any wheelchairs, we're going to have to pay that $500,000. Plus, well, it depends on how many wheelchairs. Each wheelchair is going to cost you $400. If we sell X wheelchairs, X is the number of wheelchairs, then 400x would be how much it costs to make those 400 wheelchairs. And this will give us our total cost. Now what about the revenue? We're selling them for $600. If we sell X of them, then we'll have $600X for the revenue. Now what did we want? We want the break-even point. So that means 600x, that's our revenue, equals $500,000 plus $400x. Solve that for x, and we've got our break-even point. Subtract 400x on both sides, and I've got 200x equals $500,000. Divide both sides by 200, and let's see what we get. 250, 0, let's see, 24,000. I think that's right. Let me double check over here. These are pretty big numbers. So if I'm dividing, those zeros will cancel, those will cancel, those won't cancel, and I have 2,500. Oops. Yeah, 2,500. Ooh, that was a mistake, wasn't it? So we're going to have to sell 2,500, excuse me. I'm not doing too well on my feet here. 2,500. So I need to sell 2,500 wheelchairs to break even. Tough business, I guess. All right, so we've done all that. There's the cost function, the revenue function, to break even. Those two are going to have to intersect. Set those two functions equal to get the break-even point. And there's our break-even equation. Solve it. There's our 2,500. And remember, this is wheelchairs. Substituting 2,500, both of them, we get the revenue, and we can get the cost, and you can find that 2,500 wheelchairs will bring in $1,500,000, and we'll break even. We're not losing that. Very important. There's a graph of those two equations. Here's the cost function right here, and there's the revenue function. And here's the break-even point right here. So until you get to that point, you're losing money. Once you get past 2,500 wheelchairs, you're starting to make money. And that, folks, we've already talked about the profit function, so we don't need that again. And we are done. I hope you stuck in there for the whole thing. Maybe watch this second time to pick up some of those things that you weren't quite so clear about. Well, I'll see you next time, and we'll talk about another part of functions. You take care. Bye.